Hello students, this is Dr. Ben. I'd like to take a few minutes to finish up the discussion that we were having about the kinematics of uniform circular motion. So we have this picture that shows us the geometry of the velocity vectors in uniform circular motion, and we see that the length of each of those vectors is the same, which we expect if the motion is in fact uniform. But the direction of the velocity vectors is changing, obviously, in the three positions. And so, even though this is uniform motion, it is accelerated because the direction of the velocity is changing. So what I'd like to do for the moment is to imagine that we consider one rotation of the particle from a spot back around, one complete rotation. So one complete rotation. And what I'd like to do is to derive an expression for the angular velocity in this situation. So the definition of the angular velocity would be the angular displacement divided by the time that elapsed. And if we apply this to one complete revolution, then the angular displacement would be 2 pi radians, because the particle, this one for example, would go around the circle one complete time, and then we would divide that by the time interval that motion takes, and the symbol that we use for that time interval is a capital T called the period. So I'll leave the units out so we can write this expression in algebraic form. And so the relationship between the angular velocity and the period is given by 2 pi over the period, and we see that we derive that by using one rotation. All right, so let's take it a step further and see if we can figure out how the speed relates to the angular velocity and also the geometry. And we should draw on here that the radius of this circle is r, and for this particular case we'll use the symbol omega for the angular velocity. Alright, so let's switch colors and remind ourselves of how we find the speed of something. So the speed of an object that's in uniform motion would be the distance traveled divided by the time that is elapsed. So if I apply that to a circle, then the distance that's traveled is simply equal to the circumference of the circle, and the time that would be taken for the particle to go around the circle one complete time would be equal to the period, and so I would take the circumference and divide it by the period. Alright, so let's move the paper up a little bit and we'll see if we can make some sense out of this. So the speed, we'll write as the symbol v, the magnitude of the velocity, will be equal to the circumference for a circle, which is equal to 2 pi times the radius from geometry class. And then again we see we divide that by the period t. Alright, so if I rearrange the terms just a little bit, I'll take the 2 pi over t and put it in a bracket and multiply that by r. We see that 2 pi over the period is simply equal to the angular velocity omega that we figured out before, and then that would be multiplied by the radius. So this is a very important relationship that gives us the connection between the angular velocity and the linear velocity of an object that is undergoing circular motion. And it is that the linear velocity is equal to the angular velocity multiplied by the radius. Alright, so let's take a couple minutes just to make sure we understand the ramifications. Alright, so back to our original drawing. For this situation, the circle has a radius of r, and the angular velocity is omega. The linear velocity is v, and the period of the motion is t. So those are the parameters that specify this particular motion. So first of all, let's imagine that we have a particle that is undergoing circular motion, but that the radius is smaller. The radius of the orbit is smaller. So I'll pick this same point down on the lower right-hand side that I was considering before. And so, since we just derived that the linear velocity is equal to the angular velocity multiplied by the radius, we would expect that the linear velocity would be smaller if the particle is undergoing circular motion about a smaller radius. So if I was going to draw a velocity arrow to scale, it would be shorter for this particular case simply because the radius is smaller. All right, and if we would figure out the distance traveled by the particle when we go around the circle, it would be smaller for the smaller circle, so therefore a smaller distance traveled in the same amount of time would give us a smaller velocity. What would happen, though, if we imagined that, go back to our original case, and that we changed the angular velocity from omega to 2 times omega? So that means that the particle would be going around the circle twice as fast, and we would expect that our velocity would increase. And just to check that, we see that the velocity is directly proportional to the omega, and so we would expect that those quantities would change in the same way. So if I redraw the picture, so if I take the circle of a radius that was the same as our original situation, so that's going to be r, but this time the rotation rate is 2 times omega. If I consider my point down on the lower right hand side, the velocity vector that I draw now is going to be much longer. It should actually be twice as long as the velocity vector in our original case. So we see that both of these factors impact the size of the velocity of the object, both the angular velocity and the radius.